successful transition to circular economy requires companies developing specific capabilities for circular economy. They are defined as the combination of appropriate skills, knowledge, and abilities glued together by various relevant organizational processes, routines, and bonding mechanisms necessary to develop, adopt, and implement CE strategies successfully. Circular economy capabilities can be distinguished into two main groups: ordinary and dynamic capabilities. Ordinary capabilities refer to the operational skills, abilities, competencies, and knowledge required to develop and implement CE strategies. These include employee abilities in performing specific tasks, such as material sorting, disassembly, remanufacturing, repair. The knowledge on CE principles, strategies, and business models, and digital competencies on the use of Industry 4.0 technologies for process monitoring, quality control, and resource tracking. Dynamic capabilities, on the other hand, are strategic in nature. They focus on the ability to implement change and reorganize strategies, structures, business models, and corporate operations to develop CE transition. CE dynamic capabilities mainly refer to sensing, seizing, and reconfiguring. Sensing refers to the ability to identify new opportunities, such as detecting material inefficiency or anticipating regulatory and market shift. Seizing involves mobilizing the necessary resources, knowledge, and partnership to act on these opportunities. Reconfiguring is the capacity to reshape internal processes, realign value chains, and orchestrate collaborations that allow circular innovations to scale and adapt over time. In addition to classical sensing, seizing, and reconfiguring capabilities, CE dynamic capabilities include dynamic learning. Dynamic learning refers to the set of learning routines distinguished in internal incremental learning, where learning primarily happens in internal firm routines, and closed-loop supply chain learning routines, where the external source of learning comes from the customer in the form of product returns. A novel class of CE capabilities refer to transformative capabilities. These go beyond adaptation to changing environment and incremental improvement. They empower firms and networks to fundamentally redesign how companies and their supply chains function, interact, and generate value with circularity. Transformative capabilities include triggering, envisioning, navigating, and stabilizing capabilities. Triggering capability refers to the ability to analyze the current supply chain vulnerabilities and scan the external environment. Envisioning capability refers to the ability to conceive new supply chain configurations and experiment them on small scales. These may emerge internally through collaboration between R&D, CSI teams, and suppliers, or externally via consultants or benchmarking against industry peers. Navigating capability enables to recognize the best-performing supply chain configurations and adopt them widely. This requires coordinated decision-making among supply chain partners, the establishment of shared goals, and the alignment of incentives. Stabilizing capability refers to the ability to institutionalize the new supply chain configuration and deal with resistance to change. All dynamic capabilities require macro-level components, usually called micro-foundations. The construct of micro-foundations is used to explain dynamic capabilities in an atomic and practical way through micro-level constructs. Micro-foundations refer to those skills, processes, procedures, organizational structures, and decision rules which make up the different dynamic capabilities. For this reason, the micro-foundations are relevant antecedents of dynamic capabilities, useful to understand how to acquire and develop the capabilities. They include market monitoring, idea generation, networking, and knowledge creation. Seizing refers to business models, governance, efficiency, and collaboration. Diversely, organizational flexibility, leadership, knowledge integration, and transfer underpinning reconfiguring dynamic capabilities. Transformative and dynamic learning capabilities are grounded on a unified return process, knowledge infrastructure, identification of valuable information, and incentives. All these components are critical for implementing circular economy principles, and it is important that they should be taken into account when companies plan and reconfigure internal resources and technologies. In this regard, digital technologies are very important. Thus, it is useful to clarify how digital technologies support circular economy dynamic capabilities. Sensing capabilities are enhanced through big data analytics, artificial intelligence, and Internet of Things, which allow companies to continuously scan internal processes and external environment for inefficiency, regulatory shift, and emerging customer demands related to circularity. For example, blockchain enables firms to capture and analyze real-time data on consumer preferences for circular products, thus improving their ability to anticipate and respond to changing market conditions. Digital technologies reinforce seizing capabilities since help firms mobilize resources and design new value propositions. Cloud-based platforms, AI-powered decision-making tools, and digital twin technologies support firms in simulating and evaluating alternative CE business models, while blockchain facilitates secure, real-time information exchange with partners, crucial for building joint initiatives such as shared take-back schemes or remanufacturing partnerships. Reconfiguring capabilities benefit from the use of Internet of Things and blockchain, which improve the traceability of materials and transparencies across the supply chain. This enhanced visibility supports firms in redesign organizational structures, realigning processes, and reconfiguring supply networks to accommodate circular flows of resources, such as enabling closed-loop logistics or secondary material recovery systems. Blockchain, in particular, supports the standardization of transactions and verification of sustainability credentials, which help scale circular practices with confidence and accountability. Digital technologies contribute to dynamic learning capabilities by capturing operational and strategic data that can be used to evaluate the performance of circular initiatives over time. Through continuous feedback loops enabled by artificial intelligence and Internet of Things, firms are better equipped to monitor outcomes, adapt strategies, and institutionalize best practices, thus embedding learning into the ongoing transformation process. Finally, digital technologies play a crucial role in enhancing transformative capabilities by improving operational efficiency, decision-making, and customer engagement. Big data analytics and artificial intelligence are essential for processing large datasets, helping companies identify inefficiency in manufacturing processes and understand consumer behavior. The integration of cloud computing, big data analytics, and artificial intelligence enables companies to gain valuable insights, driving innovation and improving their ability to circular economy transformation. Additionally, blockchain, Internet of Things, and cybersecurity technologies enhance stabilizing capability by allowing companies to track products throughout their life cycle, ensuring authenticity and providing transparent information on product history through digital product passports. Additive manufacturing contributes to the development of envisioning capability by enabling the rapid production of prototypes and customized products, supporting innovation and product development. Artificial intelligence also plays a vital role in the navigating capability by helping managers make informed decisions about new configurations and management strategies. Product lifecycle management systems powered by Internet of Things and artificial intelligence optimize product design, production, and disposal strategies, making supply chains more efficient and adaptable. The adoption of artificial intelligence, big data analytics, and Internet of Things technologies facilitates better data collection and integration across supply chain partners, enhancing collaboration and enabling large-scale transformative changes. In digital marketplaces, virtual reality technologies allows customers to interact with and customize products in virtual showrooms, improving the customer experience and driving satisfaction and loyalty. In conclusion, understanding and developing circular economy capabilities is essential for the successful implementation of circular economy strategies. Developing strong circular economy capabilities should be a fundamental focus for companies aimed to compete in eco-conscious and sustainable systems.